we're going to be talking about undervalued engines. And first, we're going to go over a little bit of history. I'm going to start basically in the 70s and 80s. Basically, all we had was OEM cylinder heads, iron heads. So basically, back then, everything was undervalued, underported. I mean, you were limited on engine speed, you were limited on camshaft technology, you were limited everywhere. So everybody just got out their head hogger 2000 and made everything as big as possible. And that was the only real way to increase engine speed at that time. And then in the 90s, we started getting aftermarket cylinder heads. And, oh, dang it. Bear with me. In the 90s, the aftermarket, it basically exploded. And the valve train, we got better valve trains, Jessel, T&D. We had better cylinder head intake manifold designs, but we were still lagging behind as far as camshafts. We needed better heads. The camshafts were the valve trains were a little better, but we needed better heads. And in 2010 to 2020, basically what we see now is NA normally aspirated development is dead. That pretty much died with the 10.5 rule in Pro Stock. We have competition eliminator, which is basically the last class you can race with an unlimited NA engine. Nowadays, everybody is going power adder, bigger engines, bigger displacement. Power is the only goal. And why? Because basically it's 1/3 the cost. And now we have head and manifold designs that 20 years ago I could only dream of, and cams and valve train technology as well. And now the cylinder head technology is a little bit behind the valve train technology. We can push things further than we ever dreamed of nowadays. What I'm going to talk about a little bit is a discharge coefficient. Anybody doesn't know what a discharge coefficient is. Basically, this is a way to rate the efficiency of a port or a valve or any cross-sectional area. And a coefficient is basically an equation that defines some property or characteristic. And the property or characteristic we're trying to define is, what is 100%? What is the maximum flow potential I could possibly get out of this given cross-sectional area? And the one I have up here is for the throat area, which is the smallest area in the system, or actually it should be the smallest area in the system. So if we look at the 70s and the 80s, those ports and the throats were basically about 65 to 70% efficient. And at that time, you could mess up the flow, you could mess up the valve job a little bit, the combustion chamber, the cross-sectional areas, and it wouldn't have a huge effect on the engine's power band. In the 80s and 90s, the induction systems got to be about 75 to 80% efficient. And this is when everybody really started with seats and throats and back cuts and tuning the venturi section and getting everything as efficient as possible. So if you mess the valve job up or a cross-sectional area, it could cost you 20 horsepower pretty easily. But nowadays, these ports are designed right up to 90, 92% efficient, which means they're on the razor's edge. Every single port design that we do, or induction system column that we design, is specific to the engine combination that is being used, and whether it's truck pull or drag racing or undervalved or overvalved, which we'll talk about here in a little bit. And I want to make a point of the fact that the valve jobs that you see today are so finely tuned and on the razor's edge to get to this 90 to 92%. And I see this routinely, and probably I see it once a month at least, is you will get a high-end cylinder head from us or MBE or Foltz or somebody like that, and then take it to somebody and get a valve job on it and wonder where your 0.2 of a second went and your mile an hour. Because the throat itself is the most critical area. We'll talk about that here in a little bit. I'll show you the most critical areas in the system. So if you look at, and I use a 500 cubic inch Pro Stock because as far as NA power is concerned, it's probably the most efficient there is. And turn in 10,000, making 1475, and you're making 2.9 horsepower per cubic inch. Now what happens is, as we increase stroke, now a Pro Stock engine is over square. Its bore is much bigger than its stroke. So you're limited by your bore spacing. So in order to gain displacement, the only real way to do that is to add stroke. And as you add stroke, you make the engine more under square. and you raise your piston speeds, and the more you do that, the efficiency takes a nosedive. It starts a nosedive rapidly and very quickly for two reasons. One, the amount of valve area that you have to feed the amount of cubic inches is directly proportional to the bore size. You can only fit so big a valve within so much bore. So if you're set on bore, you're set on valve size. And if you're set on valve size, you're set on flow potential. And there's no way around that, except with the camshafts, which we'll talk about here in a little bit. So here we have an equation. This is what we call the CFM demand, or PPCD, peak piston CFM demand. And what this is this little formula spits out how much air this engine is requiring at peak piston speed at 76 degrees after top dead center, which is the fastest piston speed in the cycle. So if you look at a Pro Mod engine, which is the epitome of an undersquare, undervalved engine, it is the most undervalved engine design on the planet right now. It is those cylinder heads flow 715 CFM through a 2760 valve. Now that's a lot of airflow potential, but if you look at this engine, this thing's requiring 700 CFM at its torque peak, and it's requiring 877 CFM at its power peak. So it's 150 plus CFM undervalved. The engine is asking for more air than the valve can supply. Now, without a 1,250, 1,300 gross lift and extremely fast piston speeds, these power levels that we see today and all these undersquare engines would be impossible. With the 60 millimeter cores, we have valve speed that we can open the valve really quickly. And the whole idea here is to get the valve into a higher lift area at max piston speed for a longer duration of time. The engine's choked off, so if you just lift the valve and shut it, it's only at peak piston speed for a given amount of time. But if you can slam it open and hold it open during that period, you're exposing more area. So you're getting more air in the engine over time. The draw is a longer draw. And that actually changes the manifolding, it changes a lot of things. Remember I said the bore itself restricts the valve size. And why is that? When you're working with the discharge coefficient, which is the amount of flow per unit area for any given cross-sectional area, when you start increasing valve size, you get that valve more and more shrouded off. It gets closer to the bore wall. So the bigger you make the valve, the more the discharge coefficient noses over. It makes it less and less efficient. So in a normally aspirated engine, these are the guidelines that I've always used for the last 30 years. So basically a wedge engine, the intake valve would be 50 to 51% of the bore diameter. Now, can you go bigger? Yeah, you can go a little bit bigger, but these are numbers that are safe. This is a rule of thumb. It's not a law. It's not a hard set rule. But I know that if you only go 50, 51%, I know that valve is going to be unshrouded enough and have a high enough discharge coefficient to efficiently feed the engine. And by efficiency, I mean, what happens if you put too big a valve in the engine? Well, even though you put a bigger valve in the engine, you will see an increase in flow, but you will see a drop in the flow per unit area. You will actually see a drop in the discharge coefficient. So you're making the whole inefficient. And if you put too big a valve in there, the engine is lazy on the shift. It won't accelerate as well. It won't pull fuel, and it won't. And especially when you shift, it'll lag on a converter. It'll do all sorts of nasty stuff. This is directly proportional to how well that engine pulls fuel and accelerates down the racetrack. The more efficient it is, just so long as you match the engine's airflow requirements with the valve size. Now, like if you look at a Pro Stock or Comp or any unlimited NA engine, peak power is matched with the flow potential of the valve. So 640 CFM will make peak power at about 10.1, 10.150. Now, if I try to make peak power higher than that, now I'm past the efficiency curve. So you don't want to do that on an NA engine. On an undervalved engine, that's a different story. Now the canted valve, you can go 52, 53.5%. And the reason that is because the valves are canted. They're moving away from the cylinder wall. So you can shove the valve diameter out a little bit and decrease the efficiency down low a little bit and gain up top. And the rotated canted valves, like you see in Pro Stock and a lot of the heads nowadays where the valves are rotated, basically like what they call the semi-hemi configuration, you can shove basically as big a valve in there as you can without them clipping. And one of the reasons is, I wasn't going to get into this, but as you rotate the valve around, the short side is now aimed right down the bore wall. Like a Hemi, the hemispherical head has the valve right on the bore wall. So as it opens, the bore wall becomes an extension of the short side. So it has good pressure recovery. And by pressure recovery, I mean it controls the deceleration of the air into the combustion chamber. So when the valve opens, you want that cylinder, that combustion chamber tight to the valve. So as it opens, it sees an incremental amount of area as it opens. It's controlling the deceleration of the air. If you just laid the whole thing back and the valve opens, all it would do is boil and turbulent and actually shut the flow zone down. It actually makes less torque and less mid-range power when you do that. Now the valve diameters in an undervalved engine are a bit touchier because you can go 1 or 2% more. And to put that in perspective, I mean 1 or 2% might be 50 thousandths of valve diameter. So this is how close to the edge we are of falling off that cliff of the efficiency and hurting the engine. An undervalved engine is requiring more air than the valve can supply. So it's screaming for more area. It wants more area. So if you have a long draw at peak piston speed, get the valve into a high lift area, the depression on the throat is X amount. So if you make that bigger, the depression drops and you can get more air through the motor. Even though you take a hit in efficiency. This is something you would never do on an NA engine because you would see it. But since an undervalved engine is screaming for more valve area, that bigger throat, even though you take a little hit in efficiency, is actually going to get more air into that engine. And you can look at it to use, it's analogous to gaining cubic inches. The more cubic inches, the more displacement you throw into that engine, the less efficient it gets. Like a Pro Stock will make 2.9 and a Pro Mod makes 2. So it's the same thing. Even though you're hurting the efficiency a little bit, you're still getting more air in the engine and you're still going to make more power. Now, if the valve, let's say you make the valve bigger and you gain 50, 60, 80 horsepower, if the valve in a perfect world with the right size bore, you'd gain 150 horsepower. A quick and dirty coefficient is the CFM per square inch of valve area. We use this every day. When we talk about cylinder head flow potential, valve flow potential, we are always talking CFM per square inch of valve area. And for any given cylinder head, 118 CFM per square inch of valve area is the most I've ever seen, most Preston. I mean, that's about the most you're going to get out of anything. And this is the equation. Now this is, I'm going to show you the difference between a tuned NA engine and an undervalved engine, and the difference in the CFM per square inch of valve area, the drop in efficiency, as you can see. Preston's going to be talking about the actual engines that we dynoed and showing you the dyno graphs of what happened when we do this. With a 250 valve flowing 460, it flows 115 CFM per square inch of valve area. Now you stick a 2300 valve in there and it's shrouded off and it becomes less efficient, but you're still gaining a little CFM. You've gained 10 CFM. Now let's see hold on a second. Let's see what it would do if it wasn't shrouded off. Yes, if it wasn't shrouded off and the efficiency didn't take a hit, that 2300 should flow about 480, 485. Now this is something that everybody should keep track of when you're changing valve size or going to a bigger valve size. One, you have to know how much air the engine is asking for. That's number one. Two, how efficient the valve is. And of course, we also rate the efficiency of all the cross-sectional areas all the way up the column, not just the valve. But the valve is the quick and dirty one. You know right away if that port is actually moving enough valve area or airflow around that valve. These are all the coefficients and the variables that we keep track of within the intake column and the port. So to let you know that this is just one coefficient that we use, but it's the what I call the quick and dirty one that anybody can use. Now we're going to talk about the difference in port design for undervalved engines, because as the engine requires more air, the port dynamics and the actual port shape change with that. So if you had an engine and you added 100 cubic inches and it's now undervalved and you have the same port design that was optimal for an unlimited, just the NA application, it is now not optimal for the undervalved application, and I'll show you why. And I use the small block Chevy and the big block Chevy ports as an example, because here you see the floor has a hook in it, and this is what we call a hypercritical short turn, because the air speeds here are really, really high, and you have a velocity gradient right through here. In other words, all the flow is on the roof, and the floor is dead. So when you see this scenario, you have to make the areas that turn the air over the short side much bigger than would have otherwise been necessary. When you instill velocity gradients, hooks, bends, short sides, tall short sides, you have to make things really big than would have otherwise needed in order to turn the air efficiently around that short side. Now it will function, and you can have two ports on the flow bench. I've seen it many, many times. If you have your short side too tall and abrupt, you can just blow the bowls out and slow it down over the short turn, and it will flow the same amount of air as a one that is properly designed. But the one that has the airspeed spiked, something like this, will nose over much, much quicker, 1,000 RPM sooner than one that's laid back and designed properly. Now, as the port raises, or goes up, you raise that port up, you see the velocity gradients are minimized a bit here, and we don't have to make the area to turn it around the short side too large, or larger than would otherwise been necessary. Now, in an undervalved application, this is more along the lines of what you want. You want a swoopier port. Is that a word, swoopy? More aerodynamically intuitive. It's dove down at the valve. It has a more line of sight, because the air speeds are so high it doesn't want to turn. It's very, very difficult to navigate turns with the airspeed being that high for that long. So we try to design the ports to enter at the valve very smoothly with no abrupt changes in area or direction. This area right here is the most critical area in the entire induction system. 75% of our effort is from the apex of that short turn right there to that combustion chamber. This is a tuned Venturi section right here. It has to flow at all lift increments from 100 all the way up to 1,300, and it has to be efficient at each one. And when I was 19 years old, I asked Richard Maskin, where does a port need to flow? Does it need to flow up high? Does it need to flow up low? And his answer was very simple. It needs to flow everywhere. You can't take a hit anywhere, no matter what lift you're at. You can't hurt it. And a lot of people will go in and start working in this area, especially gasket matching. That's probably the worst thing anybody could do to a cylinder head, because gasket manufacturers, if you didn't know it, they don't know what size port you need. They're just making them big enough to fit anything. So we port match. We actually design the opening to be a certain size and then actually match the manifold to it. We don't really care what the gasket is. Now, seeing as how this area right here is the most critical, right in here, any small change to a highly refined port is going to have a significant effect on power and airflow the engine's ability to accelerate, handle a load, and pull fuel. If you blow this area out too big, or it's misshapen, or this combustion chamber is not at the right angle to the valve, it's not uncommon to lose 30, 40, and I've seen 60 horsepower right down the tubes, because people will blow the throat out or change the angles that were otherwise matched, and now it's out of tune, because this area is absolutely tuned. 25 years ago, I kind of came up with the 90% rule. And when I said the throat should be 90% of the valve diameter for any given engine combination, that's the safe plan. I know that if everybody here put their throats at 90%, basically I don't care what lift you have or whatever, you're safe. It's not optimally tuned, but you're safe. Any bigger than that, and you're kind of playing with fire. Now, most engines, I would say the majority of engines that are not undervalved, if you go to a 92, 93% throat, I have seen, again, up to 60 horsepower loss. 30 is normal. 30, and it mostly takes a hit in the torque department because you're making that area too big. You're slowing the airspeed down. So that is a loss in signal. Everything moves from high pressure to low pressure. That throat is a given size at a given airspeed, so it's a given depression. So all the air will move towards that point. If you kill that airspeed, you lose your signal. The air doesn't want to move towards the cylinder. And that's what I'm referring to. Now, these are general rules of thumb. It's not written in stone, but this is pretty much what we go by. 90% is excellent average power and throttle response. You probably never go wrong putting your throats at that size. Now, 91%, well, yeah, it will add a little bit more power, unless you have a real low lift cam. Now, this is really directly proportional to cam lift, gross lift. So if you had a 500 lift cam, a 91% throat is not what you would want to do, because the valve is so close to the seat that you have to set the air up for the turn. So the throats have to be small in order to set that air up for the turn. If you make them big, it just rams into the back of the valve and boils off, and you shut the flow zone down. The whole idea that size and that shape is to set the air up for the turn around the valve. So 91.5% is only used in 750 or lift or higher camshafts. 91.8, every unlimited NA engine I've ever worked on, I always took them right to 91.8. Now, I know 91.8 sounds arbitrary, but it's safe. I know that's safe. 92 is on the razor's edge. That's right there is where you could fall off the cliff really, really easy and hurt that signal. And again, that with a 1-inch cam, I would not go with a 91.8 or 92% throat unless you are at least 1-inch lift. Now, 92% is dangerous. Nobody should ever put a 92% throat on any head that isn't an unlimited NA or severely undervalved with a high lift camshaft. The 92.5, only in the last 10 years have I ever seen an induction system respond positively to a 92.5% throat, and that's because the engines are becoming so undervalved and are requiring so much more air than the engine can ask for. So we can take a little bit of a hit, and you got to remember that the difference between 91 and 92 is maybe 10 thousandths of an inch. This is what we're playing with here, 10, 15 thousandths. This is how critical this is. And I wanted to incorporate this with 4-valve heads, because 4-valve heads are a different world. They're almost never undervalved, but they are hypercritical on the throat. Because they have so much valve area, you can make the throats too large extremely easy. For a 4-valve head, an 86% throat, that's safe. I don't care what valve head, 4-valve head you have, 86% is dead safe. You will never go wrong. 87%, it does add a little more power, but you better have about 400, 420 lift at least. And 88% seems to be the best overall power band between 4-valve heads in the 400 to 450 lift range. A lot of the heads nowadays have too big of throats right out of the factory. And it's not uncommon to shrink them up and see 20, 30 foot-pounds of torque instantly. And throttle response, coming out of a corner, accelerating, falling back on a torque converter. Because if you make things too big, you'll lag on the converter. You'll come back on the converter and it'll just hang there before it accelerates. But if you make things reactive, the proper plenum size, proper air speeds, and the proper depression at the throat, it'll react instantly on the shift. Then the 90% rule, like an LS head or any 23-degree head with 600 lift or higher, this is 4-valve. 600 lift or higher on a 4-valve, you can use 90% on the throat. But not many 4-valve heads have 600 lift. That's kind of uncommon. If you go to 91% on a 4-valve, you will suffer torque loss. You will suffer loss of acceleration as well, unless you are 600 or higher lift. And 91.5 is like running 93% throats on a 2-valve. I kind of went through that pretty quick, didn't I? Okay, is there any questions? We're going to take a little questions and then we'll get with Preston's.
What's the best way to measure that throat area?
I just use expanders. Now, where that throat area occurs is related to the valve angles being used. So if you have a 45-degree valve angle and you cut that 15 degrees, the throat itself will occur about 280 thousandths down. If you use a 55, what that does is the 55-degree valve seat makes the throat bigger. You could shove it out, but it moves the apex of that down. So that it gives the air more time to set up for the turn. So that's how we get away with 55-degree seats. It's the smallest area underneath the valve. And I usually just use expanders and sit there. And in unlimited NA engines and even now undervalved engines, the throats aren't round a lot of times. No, the majority of the time, and by the way, never bore a throat. The one way to kill a head faster than anything is try to bore 90 degrees. That will destroy the flow characteristics of just about any cylinder head on the planet. The valve throats themselves are not perfectly round. They're ovate, they're oval, and they're moved towards the bore wall. So they're away from the wall, I'm sorry. So basically, if you look at it, you would have all the, let me go back here. I'll show you. So basically, you'd have back here, you would have 5 angles visible. And here you'd have 1. Because the whole thing is moved back, oval, and over. So what you're doing is you're accenting the flow zone in the combustion chamber. Wherever there's most flow, you have the most angles. Wherever there is no flow, you have the least amount of angles, which is on the bore wall. You think about it, the valve is opening against that bore wall. It's very, very close. So why would you want to turn the air into the bore wall? Take your throat out on that side and shoot it right down the bore wall. So that's how you move it over. And also the air doesn't want to turn all the way around the short turn, so you lay it back and you have little angles here, but it's turning real hard right here, so all the angles are on the back wall. And motorcycles now, all the 4-valve motorcycle stuff you see has a severe offset throat. On the short side itself, you have the seat, and on the back wall you've got 6 angles. And everything wants to move, all the airflow wants to move or flow to bore center. So the area in the combustion chamber, which would be basically from here to about right here, this is where all the angles, see how broad that is right there? See, there's no angles right here. There's almost nothing. There's a broad angle right here. This is a hard turn. This is all setting the air up for the turn. But there's almost nothing here because it's going down the bore wall. Another thing is since you're shooting down the bore wall, this is the bore wall line. See that? This wall is not taken all the way out to the bore. This is how we increase the discharge coefficient of a valve as well. Because on that side of the valve, there's very little flow. So you have a very slow flow zone. So that's where the reversion is going to act on the intake port. Where do you detonate engines? On the intake side. That's where you lift the ringlet. The reason is this area right here is lean. That's why you see it clear. That's why there's no carbon buildup over there. It's so lean that it goes off, it detonates. So what we do is we bring that wall in to up the airspeed, keep it from reverting, and if you up the airspeed, you're going to get fuel on that side. Any other questions? Yeah.
Can you please explain why it is important to keep the angles on the valve seat on the sharp edge and not round it up, and why it is never a good idea to have a round back cut on the valve?
Yeah. On the exhaust side, you can use a full radius seat. And on an intake, it's a complete and utter disaster because you can cut the air in 15-degree increments, maximum. So if you look at a 45-degree valve job, it's 45, 60, 75, 15, 15, 15, 15. That's simple. All valve jobs are that way, except when you go to the steeper valve angles. When you start going to a 50-degree valve angle, you get to cut it in 10-degree increments, which moves the throat apex down deeper into the bowl, giving the air more time to set up for the turn. By the time you get to a 55, you're 350 thousandths down in the throat, giving the air a lot more time to set up for the turn. So, and also sharp angles are what we call fuel vaporization ridges. That atomizes fuel. If you have a full radius seat, any of the deatomized fuel, especially coming off the short side, will just go right into the combustion chamber in solid form. And then what you'll have is lean, rich areas in the combustion chamber, which makes it more detonation sensitive. Next question. Yes?
Earlier we were talking about the velocity. I'm sorry, I didn't sleep, but you talked about the velocity on what is the velocity you're looking at for like next part? 260, 280?
Okay. Localized. Okay, at the throat, 136 CFM per square inch of valve area is about 330, 340 feet per second. Now this is flow bench, okay? We're talking flow bench numbers here. You want to get as close to 350 as you can, but you're not going to get there. 136 CFM per square inch of valve area is the most that I have ever seen out of any throat, just about. Maybe a Hemi will move 137, maybe 140. I think I've maybe seen that once in my entire life. But if you take your area of your throat and square inches of area, the diameter squared times 0.785, and then divide that into the amount of flow, you get the CFM per square inch of valve area. So that is one target that you should always shoot for. You shoot for that 136 at the throat. Localized velocities upstream should be no faster in most cases than 300 feet per second. And we're talking pushrod area or opening of the port. There are cases where those airspeeds are higher, super stock. You're up there in the 315 range. Nitrous engines, because we're spraying 1,000, 1,200 shot at 50, 60 degrees below zero, we drop it down to about 285, 289 because of the density of the charge. The overall average airspeed you're shooting for is about 260, 280 on a 2-valve and 330 on a 4-valve. Now, a 4-valve doesn't have localized, or should not have, localized velocity chokes. Some of them do. When you have one port feeding 2 valves, you've got an upstream choke. So you don't want those chokes to be any slower than 300 or any faster than about 320 when you're feeding 2 valves with one port. But like Indy IRL stuff with individual ports, those are 330, and those are just straight bores. I mean, you literally bore them out to where it's flowing exactly 330 and put a cork in it, you're done. Yes?
I attended a speech by a University of Michigan researcher, fuel-injected systems, and I don't remember, but I think it was for a passenger car, not a racing engine. He said, best fuel economy and best emissions, if one of the injector ports, and it had 5, was pointed right straight at the spark plug. Can you shape the port so that a certain amount of fuel right straight at the spark plug.
Absolutely,
Okay,
absolutely.
good.
Is this Peter Borum?
Speaking.
Yeah, okay. Mr. Vorum was the one that did the paper on the 2 degree of freedom system and the induction system and how those react. So might want to talk to him. Next question. Yes.
On the chamber wall, relative to like what valve angles you use, like say, do you want to vary that chamber wall if you're using a 45-degree seat versus a 55?
Yes. Yeah. It changes pretty drastically, actually.
Is it best to continue like the top, like say if the top cut is a 40, is that best to continue that same angle?
We usually shoot for about a 10 degree off valve angle, so a 40 degree chamber wall. And it depends on the valve angle. A 23 degree head is a concave combustion chamber. You've got to dig the whole thing out. Like a big block Chevy, you've really got to dig the combustion chamber out. And that is not a very good pressure recovery zone. It's not a very good design. And this is why we go to lower and lower valve angles. And once you get to 14 degrees, you can go with an absolute straight wall. And that's the best, some of the best pressure recovery you can get. And then when you go down to 10, we have a convex chamber. It will actually come off the valve like this. So instead of just it'll be, at 14 degrees, you can almost always get a straight combustion chamber. But by the time you get to 10, you're actually coming off a 55 degree seat to a 50 top cut and then going back to 45. So basically you're just building this beautiful venturi in the combustion chamber. That's the best you can get. Next question. Okay, let's hear from Preston.
Hello everyone, my name is Preston Mosher. Most people here probably don't know who I am. I'm actually pretty new to the cylinder head world in comparison to Darin over here. I've actually only been in the game here for about 8 years. So I graduated from School of Auto Machinists in 2013, and then I was hired at BES Racing Engines almost immediately after that, and I've been working there ever since. Over the past couple of years, I've grown into running the cylinder head department. So now we're going to look at several engines that we built at BES Racing Engines that were kind of less than ideal combinations. All of these engines here, they're severely undervalved at the beginning, and less severe as they go on. But they are, they're not your ideal naturally aspirated engines by any means. But this, just like what Darin was saying, this is kind of the trend with racing now. It's going less away from naturally aspirated, maximum effort, ultra high efficient engines to just plain trying to make the most amount of power that you can within the rules so that you can go faster. This first engine here is 461 cubic inch small block Ford and a 4.157 bore, 4.250 stroke. It's 15 8-to-1 compression, ran on Q16 fuel. Now this is a bracket race engine, so this engine here wasn't 9,500 RPM or anything like that. It was meant to operate up to about 8,200 RPM. Has to have longevity. Has to be able to make it down the racetrack for upwards of 100 passes before being torn down and things changed out on it. I'm going to kind of go through because we made a lot of changes to this engine here, and that's why it's pretty well and is decently documented. One thing I can tell you for sure, after going back through here and going back through all my information and everything on this engine, take way better notes than you think that you're ever going to need, because you're not going to remember it, and when you go back to look at it, you're going to be scratching your head a little bit trying to figure out what you were talking about. So I'm going to go through here and I'm going to tell you kind of the different components that we put in this engine and everything in a little bit more detail here before I actually get into the dyno sheets. So that way it left more room in the screen for the dyno sheets so you guys could actually see them really well. So this engine here, when we first started out on this engine, we started out with a 285, 302 duration at 50 camshaft on 115 LSA at about 850 thousandths worth of lift. Second camshaft that we put in this engine was 278, 304 on a 117. We upped the lift to about 950. Now the third camshaft that we ended up with was a little bit longer duration on the intake side, still the same lobe separation, still the same lift, that 950 lift. The intake manifolds that we worked on here was the Edelbrock 2868 manifold, and it was just no welding or anything like that done to the manifold. It was just completely ported out as far as it could go for this type of an application, which in the case of a 2868 on this engine it's not enough. This engine was dyno, all this testing and everything was done over the course of a few years. And so at the beginning of this, small block forwards were still pretty, larger cubic inch small block forwards were still pretty limited on the intake manifolds that you had to be able to feed that large of an engine. And that's also kind of what led to the CID small block forward manifold, was because you just didn't have anything that was good enough for these engines. So halfway in between here, we actually ended up with a CID LS manifold that we cut in half, and we changed the bank offset on it and everything, welded up the plenum and stuff to actually fit it to this engine, because that was the best thing that we could come up with at the time. Now that manifold there, you'll see here why I'm telling you that it's the worst manifold that we tried out here. It wasn't anything to do with the actual design of the manifold, it was how it was actually put together and the sizes of everything and the lengths. This manifold here had a 5.6 CSA plenum entrance, and the runners themselves were about 4.375 inches long, about a 10-inch overall runner length, and that's too short for this RPM range on this engine. Then we moved up to the CID small block forward manifold, and this was about a year or two later. And this manifold is actually made for small block forwards. And this manifold here just had a port match on it because it was actually sized correctly for this large of an engine. And it had a 5.0 CSA square inch area at the plenum. Now the 2868 had about a 4.5 inch area at the plenum. And that's about as big as you can make it in there. And it's still too small for this type of engine. That's what I was talking about. So the 2868 and the small block forward manifold, they also have very similar runner lengths. The CID small block forward is about a 1/4 inch or so shorter than what that 2868 was. So the cylinder head modifications here, this is all on the same cylinder head. So we started out with a set of Edelbrock GV2 cylinder heads. If anybody knows what that is, that's an inline valve small block forward head. It's a very high port height and everything. It's more or less as far as you can take an inline valve cylinder head on a small block forward. So our standard port that we started out with here was a 2200 intake valve. There's a 1600 exhaust valve, had a 3.7 CSA port entrance on it, and it was about 115 CFM per square inch of valve. So not absolute max on what you can get from that valve size in this, but just the limitations of the actual casting and everything, and an actual valve placement kind of limits that. And that's one thing you have to take into account with certain castings. You just can't get 118 CFM per square inch of valve with some castings. So then we also made this port larger. So we also went to 3.8 CSA, same size valves. I upped the port entrance, and then I just made the entire port itself bigger. We had the short turn back, I deepened up the bowl, and it just when in doubt, hog it out. I got out the head Hogger 2000 there and kind of just want the town on it. Then the next iteration of it was I filled in the long side of it with epoxy. So basically what I did here was the entire roof line of the port, leading from the port entrance all the way down to the valve job, I epoxied up. And so obviously at the beginning, because it still maintained the same cross-sectional area, it kind of started out very thin there, and then it got thicker as it went through the long turn. Now when I did this, I also biased the long wall on it. So if you're looking directly into that port from the combustion chamber, straight down at the valve, with the exhaust, basically the exhaust ports facing towards you, if you were to look at this, you would see that that on the long side there, the closest to the exhaust valve was filled in less than it was on the other side, and so it was about 100 thousandths bias. So it was filled in about 200 thousandths on the exhaust valve side of the valve, and then about 300 thousandths on the bore wall side. And I'll get in a little bit more why I actually did that and what it did to the head. And then the last variation over here was we made no other changes to it. All I did was move the intake valve 40 thousandths away from the exhaust valve, and we put a 2275 intake valve in it and had very little airflow gain, about 10 CFM at the top. And with doing this, that actually dropped that CFM per square inch of valve down to 110 CFM per square inch of valve with it. It gained nowhere near the amount of airflow that it would have needed to still be efficient. So here's our baseline test. This is with that 2868 manifold, the number 1 camshaft, 285 on a 115. Now, as you can see here, this isn't a terrible engine by any means. You're making about 930 horsepower here, and it's peaking at about 7,600 RPM, 75, and it makes 702 foot-pounds of torque down to 6,000 RPM. That's nothing to sneeze at, but with this customer here and the class he was running and everything, he needed about another 80 horsepower to be able to run what he needed to do and not be killing the engine while he was doing it. And so we set off on a quest to be able to get that 80 horsepower out of it. So this next test here, all we did was just change camshaft. And so this was that 278, 304, and a 117. Now mind, this is now 950 thousandths worth of lift. So that valve speed and that valve action has gotten a lot faster because we've actually shortened the duration on it, and it has more lift. So that valve, in order to travel the same distance in a shorter period of time, has to move faster. And you can see down here at 6,400, it didn't lose any torque or anything like that. If anything, it gained torque down low, and it RPM'd higher. And so now we're up to about 7,900 RPM max at peak power, and we're up to about 985 horsepower. So we're getting close. We made that one camshaft change things around quite a bit. So we picked up 19 horsepower and 14 foot-pounds of torque on average from 6,400 to 7,800. Now I'm going to try to keep the averages in the same range so that, because we do, as we go on here, we do actually RPM this engine higher, and if I just average it all the way through, none of those averages make any sense. With the third camshaft, we went to 288, 306, still on a 117, same lift. So we elongated that intake duration. And what we were trying to do at that point was to get it to RPM just a little bit higher. We're trying to get to that 8,000 RPM mark. And we just about did that there. I mean, so right there, it's making 996 horsepower right at 8,000 RPM. We still didn't lose any low-end torque, picked up just a little bit. So we're at another 14 horsepower, 4 foot-pounds of torque average increase. So now we realized that once we did this, that we still had a restriction in the system. Obviously, it wasn't a camshaft anymore. Could we have changed the camshaft around a little bit more and gained a little bit extra power and stuff? Yes, we could have, but as you can see, it's kind of diminishing returns here at this point. And so we decided to try to attack the restriction. Obviously, it's in the induction system somewhere. And so when we moved on to the next test here, we went to the larger cylinder heads, and we also changed up the intake manifold. And we went to that cut-up LS manifold. Now, at first, it actually looks like this was a win, because now at 8,600, we're making 1,000 horsepower, and this thing is definitely RPM and higher. Keep in mind, this is beyond what we wanted to RPM. But if you look down here at 6,600, we were making 650 foot-pounds of torque down there. So that intake manifold and the cylinder head combination here absolutely killed the bottom low end torque. So these undervalued engines, they do operate a little bit differently from an ultra-high efficiency engine in a couple of areas, but not everywhere. So you can't just go throw in the biggest stuff that you absolutely can at them and expect them to just pick up power everywhere. You still need to maintain that airspeed throughout the induction system. And when we went to that shorter runner length and that larger cross-sectional area, like I said, there, it just killed that bottom low end torque. You couldn't run this thing at any point. You couldn't average it at any point through that RPM range and have it be better than what that previous test was. So we had to figure out what it was. Was it cylinder heads that killed it? Was it the intake manifold that killed it? So the next test here, we put the 2868 manifold back on it. No other changes. And so you see here, we picked up 25 foot-pounds of torque down here at the bottom. And it pretty well carried that all the way through. And the RPM peak came right back here to the 8,000 mark, and we're at 993 horsepower there. Now, so there was a 22 horsepower gain and 16 foot-pounds of torque increase by switching back to that 2868 manifold over that really short, big manifold. So now we still realize, because it's nowhere near 700 foot-pounds of torque down there, so the cylinder head was also to blame. Obviously, just making it larger was not what we needed to do there. So then we shrunk up the intake port. We actually epoxied up the long turn, kind of how I said. Now, when I did this, what we actually did here was, since I got in there and I laid that short turn back and I made the bowl real big and everything. So if you were to look at like Darin's last hand-drawn port that he had on there, you see everything's kind of lean back. You're taking that turn out of the port so that high-speed air can actually make it around that turn and into the cylinder. And so that's basically what I did here at this point, was I filled in the long turn so that it laid that whole port backwards like that. Instead of being straight up and down, coming down straight down at the valve, everything is kind of leaned back like this. And now when I did this, as you can see, all of the low-end torque and everything came back. If anything, it's better than what it was. And you'll see here, it actually RPMs a little bit higher. We're making a little bit more horsepower, and it runs upstairs there just a little bit better, and it carries it a little bit further. That port is not shutting off nowhere near as early. It's much more efficient in its over rev. So now this is what we did here with the CID small block forward manifold. Now, as you can see down low, it didn't make, so this is a bigger cross-sectional area. So you can see this is approximately the size that engine wanted. So there was no loss in torque down low, but there was absolutely a pickup in power upstairs. So there's 125 horsepower on this. And it did RPM just a little bit more, because that runner length was just a little bit shorter on that. All that makes sense. That goes along with everything else that you'd read. But that also highlights the fact that when it's actually right, going larger in your induction system and stuff like that won't kill your bottom low end torque. And so now this here is with that 2275 intake valve in it. So we made no other changes to it. We just moved that valve further away from the exhaust valve, put that larger port, put that larger valve in there. So keep in mind that this valve flowed barely any more air. But as you can see, we picked up a lot of power down low. So we're up to 730 foot-pounds of torque here at 6,600. But at 8,100, we're 127. So we picked up a little bit of top-end power with it, not by very much. So you can see it's all low mid-range torque that I picked up on this. And by any means, on a smaller, more efficient engine, that would have not been the right thing. It would have looked like when we put that big manifold on there, that's what would have happened to it. But as you can see, this engine here was starving for airflow, and what we did there was actually increase that throat diameter, and we exposed more throat to it, so it could just physically move more mass air through that throat area on that engine. Here's the dyno sheets on this, so you can kind of get more of a visual representation of what's happening there. You can go kind of number blind by just staring at dyno sheets. You don't really get a feel for what was actually happening there. On the So this red line here, this was our baseline. As you can see, when we went to that secondary camshaft, it didn't lose anything down low. It just picked all upstairs. The engine just became more efficient, higher upper RPMs, and it ran out further, made more horsepower. Pretty well the same thing with the number 3 camshaft. It's just a smaller gain than before. And then this is that LS manifold there that we cut up and put on there. As you can see, the torque just dropped out of it. And did it RPM better? Yes, it did, but there's just no way that manifold is going to run. Switching to that 2868, you can see here it just picked up incrementally everywhere. The whole way through there, about 20 foot-pounds of torque everywhere, it just picked up. And then shrinking that cylinder head back up, you can see here it picked everything back up pretty well to where it was with that 3rd camshaft, maybe just a little bit better on the top end. And then these 2 tests here, this is between that CID small block forward manifold and the large valve. This large valve here, it picked up everywhere all the way up to the top. So this engine here at peak RPM was demanding 450 CFM. Leading up to that point, we didn't have that airflow, and this actually kind of brought that whole thing into its actual required CFM zone. So this is probably a little bit bigger of a return than you would see on some of the other engines that we're going to look at, but because it actually got closer to that efficiency zone that it was actually aimed for. Now, the next engine that we're going to look at here, this is a little bit further extreme. So this engine here is 570 cubic inches. This has a 10-240 deck height, 4.425 bore, and a 4.650 stroke. This is not how you want to go NA racing. This is not what you're going to design. You're not going to design a pro stock engine like this. It has a 2.350 intake valve. And this is actually a very efficient port for that valve size and everything. It does move 117 CFM per square inch of valve. It has a 1.710 exhaust. It's still only a 55 millimeter cam, because that's as big as you can fit in this. 904 tie bar lifters, but this engine made 1,250 horsepower. That's not bad, even for that cubic inch, and especially with a 4.425 bore. This has a 9,200 RPM max. This is the absolute max on this engine because you get up over 9,000 in this engine, things start to get hairy with the valvetrain. I'm going to show you why. And this setup here, this is kind of highlighting the fact that every engine that you build is its own combination. You have your own set of obstacles that you need to overcome, and you need to look at your engine as an individual. You're not going to just go straight at it and just throw the latest and greatest thing at it and expect it to pick up, because that might not apply to how that engine is actually built, what the architecture of it is, what you're doing. Now this engine here at 8,600 RPM is demanding almost 600 CFM. So this cylinder head here, I guess I didn't actually put that on there. So this cylinder head here flows about 510. That's it. So there's no way that we're getting to that 600 CFM on this cylinder head. Now, if any of you are familiar with engines and bore sizes and deck heights and everything, you probably would have guessed that this is a Pontiac. Now, I wanted to show this kind of area here because I really wanted to highlight the kind of, you can't just go, each intake, each induction system and everything is going to be its own piece. So this engine here, like if you look, these are 7/16 push rods. They're very long, and as you can see here, there's quite a bit of an angle on them. This thing has 800 thousandths worth of offset on the intake rockers, and you can actually see the push rod bumps that are still in these ports. This is also the reason why 9,200 RPM is the absolute limit that you want to run with this engine. You'll break tie bars, bad things will happen. It's not a good time, but it also kind of highlights the fact of what you can force an engine to do, whether it wants to do it or not. It may not be pretty. You may have to have completely different cam timing because what the valve actually sees is completely different from what the camshaft is inputting. So this is kind of a, so if you look at this here and you know anything about Pontiacs, you're gonna realize that's not a Pontiac valve cover. It's actually a Cleveland valve cover pattern. And if you look at this parting line right here, that is actually the top of the cylinder head. Everything above that is a plate that I made to go on top of this cylinder head. Because this engine is so big and everything, and what the area that I actually had to work with here, I raised this port higher up than you would actually probably want to raise a port in an induction system. But that trade-off was minimal in comparison to the fact that I couldn't get nowhere near the cross-sectional area that I needed if the port was down lower. And so what this did was actually pick those ports higher up in that V. So that's taking advantage of what you have to work with there. That's noticing, how that engine is actually built and working around it. If you'll notice, there's epoxy here on these walls and stuff. Obviously, that's not ideal because that is where these push rods are. They do have clearance, but they, at some point in their life cycle, while they're running on that engine, they don't have clearance. And they've broken through the port, and you can't have oil being sucked in through the intake port, so you need to plug it up there somehow. So this is the dyno sheet for this engine. So up to this point, you're probably thinking, wow, that is not a great engine. This thing's probably a terrible down low. It doesn't want to run, whatever. But this is also a very refined combination. We've worked on it for years, and this is kind of a representation of all the small horsepower gains that you'd have on an engine that you've built multiple times and picked up power. As you can see here, this thing makes 1,210 horsepower at 7,500. It's making 1,230 at 88. It peaks at 8,600 RPM. Now, keep in mind that this is almost 100 CFM down. And I think that also kind of lends itself to you pretty well run into that maximum amount of airflow that this thing will actually achieve. And if this was something that had a much larger bore or something on it like that, yeah, absolutely, it would make 1,300 horsepower plus. It'd be 1,350 or something like that. And so that increase would be higher right through here, so it would just keep on climbing. But because this thing is so undervalved and there's so little airflow available, it's running with a cork in it, more or less. And that kind of highlights it. But this, it's not necessarily terrible. You have to gear the car differently. You have to take advantage of what you have. So here's the actual dyno graph on it, and that kind of gives you a visual representation of how flat that is. So definitely not how you would build an engine, ideally, not what you're looking for and everything, but as you can see, like you can most certainly make this stuff work. And if you were limited in some way, shape, or form, having that larger cubic inch is not always a bad thing. Like we were saying before, larger cubic inches, you're typically making more horsepower. Is it the most efficient way to do it? No, not by any means. So this next setup here, this is actually two twin engines, basically. Both of these engines were almost identical to each other. They had the same camshaft, same compression ratio, same intake manifolds, as close as they could absolutely be. Everything was pretty well identical on these engines. The only difference between these two engines were the cylinder heads. This first engine, so this is a 547 cubic inch small block Ford. Obviously, this is a custom billet block, 10.2 deck height, 5-inch stroke, 4,155 bore. With the Edelbrock SC1 cylinder heads here. Now this engine is demanding 508 CFM. That's 7,600. This Edelbrock SC1 cylinder head here has a 2,200 intake valve, 1,600 exhaust valve. It flows about 460, 465 CFM. It's right there at 117 CFM per square inch of valve. Is by no means a bad cylinder head. That runs extremely well on properly sized engines. This engine here, this was not actually a max effort NA engine by any means. This is a power adder engine. And so it could make more horsepower with these heads, but for other limitations in the build, that's not what it was intended for. As you can see here, 7,600, that's where this engine stops. This is, and you would expect with 460 CFM, and a small box should run to 8,800. It should, it should run right up there. But this is where it hits that cork, 7,600, and so obviously that's its limitation. We won't. So on the next engine, it's actually set up with the CID SE2 heads. Now, if anybody's ever seen these heads, this is a kind of like a this is a much more upgraded version of an SE1 style cylinder head. So the valves are rotated around further. It's more of a semi-Hemi style cylinder head. It's running a 2,300 intake valve and a 1,650 exhaust valve. This cylinder head here moves 497 CFM at an inch. It's rated at 118 CFM per square inch of valve. Still an extremely efficient valve. Cylinder head, and it's on a 4155 bore. That's what this cylinder head was created for, is more or less was large cubic inch engines on that small bore. Now, since this engine, we were a little bit disappointed with this setup because it didn't pick up nowhere near what we were expecting. So we were expecting like a 50, 60 horsepower gain from this valve size increase and the airflow increase. But we were actually only achieved about 30 horsepower on this. And that kind of leads to what Darin had said earlier about if your induction system is 100% efficient and you were to make a 50 CFM gain, you're going to pick up upwards of 100 horsepower. But because this induction system is not that efficient, nothing here is actually operating at its peak efficiency, that larger valve and everything didn't net that larger gain. You can go to a larger valve and everything in it, and you're still limited in it. But you are making an increase. Here's the dyno sheets for these two engines. As you can see here on the top side and the bottom, the power kind of dips. Now this is on our new dyno there at the shop, and it's not quite as refined as the older one was. And the dyno is actually having a little bit of trouble controlling these two engines at these points here. So as far as the down low numbers and everything, I find that kind of irrelevant. I would expect these two engines to make almost identical power down low. And up here in the top, as you can see, it just picks up all the way across. The torque curve actually becomes a little bit flatter. If the dyno was actually controlling it a little bit better, it would have probably RPM'd up to 7,750 or something, actually making peak power up there closer to 8,000. So I also wanted to make sure that we got you put these equations up here for you so that you could kind of remember them and write them down and actually figure some of this stuff out a little bit better. So the first one we have is CFM per square inch of valve. So basically what you're doing there is you're taking your valve diameter squared, and then you're multiplying that by 7854, and then you're dividing your CFM by that. And that gives you the CFM per square inch of valve. That CFM demand, it's cubic inches times RPM times 0.00098785 divided by the number of cylinders. And so you can use this to kind of get an idea of if your engine is that much of an undervalved engine and whether or not it might actually benefit from something like this. By no means telling people to just go slap the largest valve that they can find and fit into their cylinder head, because 9 times out of 10 that's probably not going to be what you want to do. This is more of a tool in your toolbox to take a look at, and to help you better understand, everything that you have going on. So here's a couple of highlights here that I wanted to just point out and everything for when next time you're building an induction system. Identify your engine's weaknesses, like on that Pontiac and everything. It was the push rods, but I kind of found a way around the push rods. Literally. Exploit your pros and mitigate your cons. There's an exception to every rule. So just like what Darin was saying, for the first 20 years of his career, pretty well, you could live by that 52% of bore diameter for your valve area on a wedge type cylinder head. But as things have changed and everything, technology changes, camshafts change, all that, everything else is going to change along with it. So all these things are rules of thumb, and none of them are set in stone. So, that's pretty much it. All these engines here, all engines are unique combinations, and what it comes down to right at the end is give the engine what it wants. If you're testing an engine, pay attention to everything that happens whenever you make a dyno pull and stuff on it. If you make a change, and for some reason it picked up power, and you don't think that whatever you just did to that should have actually helped it or anything, try to figure out what just happened there. Try to quantify your results, because you'll be able to learn from it for sure. There's always something to learn from any time that you're building an engine. So no matter if you're reading some kind of a essay or something someplace, and you think that your engine needs to have this kind of a setup or whatever, and then you try to implement that, and it doesn't respond, and you do something else and it does respond, pay attention to that. That's your answer. That's the direction that you should try to be heading.
Could you go back to the first dyno graph, please?
Yes, I can.
Dyno sheet. I want to better explain. I think I've used the term choke before. I want to explain what a choke is. A choke is not the air stopping. It's not the engine's ability to produce power, just completely stopping. A choke is when the system goes inefficient. A choke is what we're doing. We're basically, why do we need airspeed? We need airspeed to convert into inertia. We convert that inertia into pressure on the valve when it opens. So it takes energy to do that. So when that piston drops and it gives me 150 inches of water, that's X amount of energy. My job is to use that energy, exchange that, or change that into inertia, and then change that inertia into pressure. A choke is when you're using more energy than that inertia can give you in cylinder fill. And as the RPMs increase, you're using more and more and more of that, so you're not capitalizing, you're not using that inertia anymore. You're just spending energy stretching the molecules out. That's what a choke is. The other thing is he pointed out...
Go ahead.
He pointed out, listen to the engine. The engine will tell you what it wants. This engine is screaming right here. The harmonics in this intake manifold are screaming at you, telling you it's out of tune. Look at this fuel curve. See how it dips, then it comes back? This is in a negative harmonic. We tune an engine for 1,500 RPM. That's about all you got. And we tune those harmonics to fill the cylinder over that 1,500. Now, if you're out of that range, you're going to get into a negative. The air wants to go backwards. And this is what we're seeing. If you look at this next one, you can see here, it starts off at 3s, and then goes to 4s, and then dips right here, and then comes back. When you see fuel curves like this, that's a red flag saying, hey, something's wrong. This is not cool. And then here, you can see the same thing. Now watch what happens as the engine tunes up. The fuel curve will go flatter and flatter. Like right here, look at that, 360s, 340s. Not near as much of a dip. And now let's get into this. Look at that fuel curve. Beautiful. Flat, ever increasing, going right up. As that engine tuned up better, as we designed the induction system and tuned all the air speeds up, that fuel curve is telling us what's going on. The BSFCs are straight, the fuel curve's straight. That's what we mean by listen to the engine. It'll tell you what it wants. All right, we're done. Any questions?
How does the exhaust tuning tie into this? Using the exhaust, pulling in the intake charge.
I think that's another 2 hours seminar.
Pretty much. Could you absolutely?
Yes, Peter.
Even with a race cam, there's very little cross flow across the valves. So it's a separate intake and a separate exhaust in a four-stroke engine.
Yes.
It's pretty much independent.
And the exhaust size, the blowdown phase is probably one of the most important factors. Because you have the exhaust, but it's like on a Pro Mod. You have a 1,200 horsepower shot. You've got cylinder pressures and heat. It's unbelievable. And with a 6-inch stroke, you're popping the exhaust off 1 inch down the bore. So what you're doing is you're initiating the exhaust gas going out, and what that does is by the time you're down at bottom dead center, ready for the exhaust stroke, you've already gotten the majority out. So you don't have to shove it out. That reduces pumping losses. So that's one aspect of exhaust tuning that's really, really important. Yes?
You said something earlier about putting an injector aimed directly at the spark plug. I remember you said spark plug waiting on wet flow is a bad deal, right? That could kill the power. So what's the difference? Why would you say, or why would you say?
Did you say injector aimed or the fuel go in there?
Fuel injector is what the University of Michigan prof was talking about.
Was that a direct injection engine, or is that a?
Direct injection, I believe, yes.
Yeah.
5 individual squirts come out of the one injector. One of them has to be pointed straight at the spark plug.
And when it comes to DI engines, I'm not even going to go there. Because a DI engine doesn't make power. They're good for fuel economy, low-end power and torque, but as far as overall max power, that's not the way to go. Plus you have valve coking problems and all sorts of stuff with them. Yes?
What's your favorite epoxy used to fill holes?
788 Z-Spar? Yeah.
Yep. Grease.
Belts on?
No, I stopped using that about 25 years ago. I mean, if you apply Z-Spar correctly, dry at the proper mix, you can't get it out with dynamite. I mean, I've
Coat it for alcohol too, I think, right?
yeah, I spray it with a clear coat, like an acrylic.
The question on surface finish and the boundary layers and stuff for different velocities, you have different preferences for?
Yeah, I mean, there's a lot of factors there, but basically, if you just had a 60 grit finish, you're fine.
For anything?
Yeah. Just so long as it's not polished. I mean, we did tests on Pro Stock engines years and years ago, and we went from a 60 to a 120, saw a little bit of a change, and then we polished everything a mirror, and it detonated the piston, boom, we went right on the torque curve. Yeah, because you're just separating the fuel on the walls and getting a lean hit.
We've also tested dimpling a little bit at BES, and for the most part, we couldn't find any kind of a power gain or anything with actually dimpling a port. If anything, it was probably a small horsepower decrease.
What about
Whatever.
when you relay a cylinder back for like nitrous and stuff, can you use that NA all right too, or what do they call that on brain dead?
So chamber softening?
Yeah.
You can on specific applications, very highly tuned engines and stuff like that, but also mainly engines that have a lot of quench pad area. So very small combustion chambers with a big bore.
Like a sprint car engine, something like that, alcohol, would that affect that?
A lot of unlimited NA engines have like 9.5 degree valve angles, so you're looking at 35% of the bore area is quench, which is too much. So you'll put like a 2 to 3 degree taper. For nitrous, you'll go all the way to 12, 14.
I've always wanted that. Thanks.
When you do that cut, like you're talking about, like nitrous versus nitrous, do you still want to leave that quench area beside the intake valve on that side, on the chamber, or on the cylinder wall side?
Yeah, usually pull off the bore 1/4 to 400, depending on the head and chamber design.
Go ahead.
You got one more too.
On topic of localized velocities in the port leading up to the valve option, can you talk about some of the instrumentation you like to use to either verify they got velocity or vector gradients, or how you like to ensure that there's a uniform velocity for the
Pitot tubes. Pitot tubes, and actually I use what's called the disruptor. And a disruptor is a vortex generator. And basically, it's just a piece of welding rod with a epoxy cone on it with a dimple in the back. So basically, you're busting the air up and dirtying it. So anyone can do this on the flow bench. If you have an area that's localized velocity is too fast, the boundary layer breaks, and you hear the turbulence, you can take that, and it's about, I would say a little more than a 1/4 inch, maybe 280, maybe 300 thousandths in diameter, that little cone on the end. So let's say your short side is too abrupt and the air can't make the turn and the boundary layer breaks and you can hear it. You can take that disruptor and go around the port, and all of a sudden the manometer will go and drop, and the flow will come up, because what you're doing is you're dirtying the air and forcing it to conform to the surface. And what you can do is you can hone in on areas. Let's say your bore wall side of your short side is hypercritical and it's going turbulent. You can take that and bust the air up and it will conform to the surface. The manometer will drop and you'll know exactly where that area is, the problem area. The good thing about using disruptors is if the port is perfectly stable, no matter where you put it, it won't affect the flow at all.
It's probably the easiest way that, actually Darin showed me that, and it's probably the easiest way that I've seen to do it.
Diagnostics with the disruptor and the pitot tube, yes.
Did you say you use Z-Spar? Is that what you were using in the ports?
Yes.
Did I hear you say you put some coating on it?
For alcohol, there's no way to keep it in there. It's going to get underneath it and it's going to degrade it. But I use a clear acrylic over the top to seal it.
What about gasoline? Is it less than-
Yeah, you don't need to clear coat it with gasoline. I've had it come back 24, 25 years. It's still in there just fine.
Do you ever use an airfoil versus a pitot tube?
That airfoil?
Yeah, airfoil off your meter as an instrument device instead of a pitot tube that turns 90. We're reading an airfoil straight. Passes.
Oh, you're talking, the pitot tubes we use measure head pressure. So it's a 90-degree bend back. The airflow is pushing, hitting the tip of it.
There's an airfoil that's straight also too.
No, I've never used them.
My second part of my question was, you said your standards are all based upon NA engines of your comparison for your percentages. Would it be your opinion that in boosted engines, it stays true, it's just the
Yes.
constant that keeps going, but the air is heavier because it's more dense?
The density of the charge is increased, but the cross-sectional areas, airspeed, all that stuff is the same. I mean, the best turbo head in the world is the same exact head you'd use for NA with an Inconel exhaust valve in it. That's it. I mean, if you go bigger, you're going to hurt it. And actually, on a turbo, you need to shrink the exhaust valve down and get the gas speed up so you can spin the turbo. Yes.
Motorsports racing class, it's got a vacuum rule. Do you still use a 15 and 30 degree top cut over your seat cut?
I have limited exposure to that, so I don't want to lead you astray, so I can't answer that question.
Most of the time, I would say if
I'd
you're
be speculating.
also if you have a vacuum rule, you're probably limited to like a factory style head or something like that. Also at the same time, so that combustion chamber probably is going to lend itself to having those flatter angles and everything. Like you said, they're more of they're scooped out and everything. So you need to try to get that air to follow that corner.
Yes.
You said the best turbo head and the best NA head are pretty much identical except for that. What about how does comparison with a nitrous?
It depends on how heavy a nitrous shot you're shoving through it. Up to 600, almost nothing changes. After 600, everything changes. The combustion chamber design, the port design, everything changes.
Yeah, I know, but you mentioned softening your chambers, but as far as the ports, obviously, with bigger shot, you can probably get more intake area or flow or whatever.
Not really. You could, what Darin touched on earlier there is that when you're actually spraying that much nitrous through there, that the density is increased by dramatically because it's 55 below. I guess Darin, you guys at Rear actually tested that at one point.
Yeah, we measured it.
And it's 55 degrees below zero, and so it's a much denser charge. And also at that same time, you're also trying. There's several other things that are actually going on there. You're injecting your oxygen into the engine at that point. When you get at that far along on a nitrous engine, you're not so much worried about running the engine naturally aspirated as you are getting it to run on all of that nitrous. And so that's why everything absolutely changes on it.
Yeah, and in NA engines, we do everything we can to speed the burn up, and in nitrous engines, we do everything we can to slow it down.
And just a point of clarification on that topic of density versus the temperature. My understanding is most of the efficiency of airflow is due to the relative speed of sound of that charge or that airflow, and that would be mostly dependent on the temperature and humidity of the air charge, not necessarily the density of the air charge.
The actual density of the charge and the temperature of that charge has more to do with the harmonics in the manifold than it does the actual airflow itself, the CFM rate of the port. Does that make sense? So let's say the harmonics of the manifold that bouncing back and forth, and you time it to intake opening. If you have a denser charge, it's going to be a little bit slower. If it's colder, the denser, it's going to be a little bit slower. So your manifold length changes, but that's about the only thing. Length and taper.
Example here with the 227 valve. How far was that to the bore wall?
That was pretty close. I want to say that it was about 150 thousandths off the bore wall.
I've heard Darin say before, target for general rule is no closer than 200.
That's right.
What
yeah.
we found is at 200, the valve is like unshrouded. It doesn't see the bore wall that much at all.
And so on an engine, on a normal naturally aspirated engine, you're right. You wouldn't want to be any closer to 200 thousandths. But that's also one of the reasons why that valve doesn't flow as much air as what it should. That's why it's not as efficient, because it's too big for that cylinder. So it's lowering that efficiency on it and actually lowering the airspeed through that. But the engine ends up hitting that CFM demand so fast and everything that it becomes reliant on the actual throat area more than that absolute airspeed efficiency.
Does eyebrow help any on that?
What's that?
Eyebrow and the block help any on that?
Oh, you mean like chamfering the top edge of the block or something to go along with it?
When your rings are only, that far down, you ain't got no room.
So if you open that bore before 220, that's
Come alive.
Yeah, that would have completely changed that thing. Absolutely.
That'd probably be 50 horse, wouldn't it?
Yeah.
that's where I was going. We probably would have saw the 50 because you had the valve area, then you could feed it in one trap.
Yeah, that's right. Yeah, absolutely. It would have picked up even more.
Yes.
How exactly did you move that over? Did you push out the guide and load in the slug?
That one there, what I did is push out the valve guide, and then because I put a larger diameter valve guide in it, so I went to a 9/16 valve guide, and this offset bore the hole, and put a bigger, larger diameter valve guide in it.
I've always used a boring head to offset guide bores.
It's a lot easier to get a straight
Yeah.
hole with a boring
Yeah.
head versus an end mill or
If
something
you use a reamer,
like that.
you're not going to
Yeah.
get it straight.
So then you move both valves over, or just,
Excuse me?
at the end you move both valves over?
No, just the intake valve. We moved the intake valve 40 thousandths away from the exhaust valve, basically getting it closer to that bore wall, just so we could fit that valve in there. Otherwise, the two valves would have just ran into each other.
Did that mess up your rocker arm geometry, by the way? Did you have the customer made because of that?
So the rollers on most rocker arms and everything are generously wide on them, and that actually put it right over to the edge of the lash cap and stuff that was running on there, and it doesn't really have too big of an effect on the longevity of it by any means. But, as long as your rocker arm, if this is your lash cap here, and your rocker arm is still on that lash cap, and it's not like hanging off over here on the side or something, you're not gonna wear it out.
Just as long as it has full engagement, you're cool.
That's right. Yeah.
One last question about that. Did the customer just come to you and say, hey, I want to make it faster, and you spit them out a number? This is business related, really. Did you just spit them out a number like, this is what it's going to cost for me to do it, or were you like, you know what, or did the customer say, this is my budget, can you work within this? How did that happen? Because I don't even know how to approach that.
Kind of works both ways.
It works both ways, yeah. Yeah, really, it kind of started out like what you said, like, okay, well, yeah, you need 80 more horsepower and you want to go faster and stuff. Well, these are the things that we can do to do that, and it's going to cost about this much. And so we made changes along the way, and we made progress and everything. We didn't quite actually get there and stuff at that point. Like I said, this was over a couple of years that this happened and stuff. So then every season he would have us do a little bit more to the engine and go a little bit further and everything along with it. Yeah, it's kind of like it's like we were talking about this before, like a super stock engine or something. Those guys work on those engines for years and years and years, and
Decades.
that's how they become so absolutely refined, is because they make little tiny gains on those engines and stuff over time. That's basically.
Yeah, I mean, you're
short
talking
version of
about
that.
350 Chevys, a standard, like a 462 head, and the ports are, no kidding, they're about that big. on there. I mean, they up the airspeed as much as they can. I mean, they'll actually put the average cross-sectional area the same size as the throat. There's no taper in the port or anything else. You get the average airspeed as high as they can and get it as efficient as they can. And still hit the CC limits too, because they're limited. Yeah, that's the super stock heads. We have what, twice as much work?
Oh, yeah.
3 times as much work, and a set of super stock heads is a pro stock head.
Yeah.
Rule package.
The rules are everything.
Rules
really.
don't lower the cost of racing,
Not
they
at
just
all.
increase them.
Not whatsoever. Go ahead, sir.
Moving all that stuff around like you're doing as far as your volume, you know, or whatever on the intake side and everything, how was that, did that affect your exhaust requirements on that?
So as far as the headers and everything, as far as actually tuning up the exhaust and stuff on this engine, we didn't hardly do anything with the exhaust. We spent most of our work. If we did work on the exhaust, is there power and everything in that side of it? Absolutely. Of course, we could pick up power there. Engine masters engines and stuff like that, especially, are a good representation of that. You can generally find a lot of average power and stuff in there. But when you're dealing with a limited budget, like what we were just talking about there with him, you kind of go after the things that where you expect to see the most gain. Yeah.
And also, speaking to the exhaust side of the engine, that's where all the energy is, okay? You've got all the heat and pressure energy in the world to work with. This is why you see that if you have a intake port that's too large, you can't cam that. You can't make up for that, okay? You can't put some camshaft in there that's going to fix that low velocity problem. On the exhaust side, however, all the energy's over there. So if you have too small of exhaust valve, you can open it early with no negative effects. Or you can accentuate the blowdown phase or change a lot of other things. You can really work, but it's numb on the exhaust side. You can gain 10 horsepower on the intake side for every 1 you gain on the exhaust. That's it? Yeah.
So you're talking about undervalued engines. Essentially, if I understand correctly, what you're saying is that the engine's drawing more CFM demand than what the cylinder head and the valve can actually supply based on the
It's the valve, yeah.
Yep.
So in looking at your guidelines, which are separate from undervalued or overvalued, looking at your guidelines on the valve diameter itself relative to the bore size as a percentage, the last one you had there was Hemi size, saying that the Hemi size is really limited by the factors as opposed to the bore diameter itself. So are we to say that, could I make the conclusion then that if I had a Hemi head, I could eventually reach a point that I could just increase the valve diameter enough that it would no longer be an undervalued engine to begin with?
A Hemi is a different world because the only thing you're limited to in the Hemi is the clipping of the valves.
And if most certainly you're going to run into some kind of a physical obstruction before you get a valve big enough to make a larger cubic inch engine not undervalved.
Yeah, that
Absolutely,
what
yeah.
head is that? The hammerhead Hemi, LS. I put a 2350 valve on those things, moving 540 in a 4-165 bore. And if the exhaust valve is smaller, I put a 2400 in it. A Hemi is the most perfect flow pressure recovery you could possibly get. It's also the worst combustion chamber in the world. And it also has.
Sorry, would that hammerhead have made more than those SC2s in that same engine combination?
That has yet to be determined. I don't know. I can't answer that.
Like in terms of the combustion shape and all that, and the Hemi head, and obviously people have done, quench areas like in the shotgun Ford motors or the Boss 9 motors, they've got, a semi-Hemi crescent head kind of thing. Maybe would that improve the situation at least?
I don't know.
Yeah, it depends on the combination, what you're trying to achieve.
Yeah, especially at this RPM range and stuff, I don't know if the Hemis generally lend themselves to wanting to turn more RPM and everything. At this RPM and everything, I don't think that the running an actual Hemi or more like the Ford Hemis and stuff would actually increase that at all.
And the true Hemi, people have tried to run them on nitrous, and everybody who tried died. They don't run.
Yeah.
They burn up. And don't ask me why, we haven't figured that out yet. But they hate nitrous, hate it. Yes?
So yeah, sorry, this might be a little irrelevant or unrelated to the underside or undervalve engines that you're familiar with, but can you share some experiences you might have with four-cylinder heads and varying the partition between each individual valve port and how some experiences you might have with that?
The partition, you mean the divider between the two ports?
Two intake valves.
So yeah,
Or two?
extending it farther up towards the manifold.
Oh, you're talking about four valve?
Yes.
Oh, okay. Most of the time, in every four valve head that I've ever worked with, like the 2JZ and something like that, I would actually take the divider back as far as I possibly can, all right to the apex of the short turn. But it's also a stressed point too, because that's supporting the middle of those two valve seats. If it was completely gone, I'd love it.
So more blunt or rounded, base
Sharp.
partition.
I've always done them sharp. I've always had the best luck of knocking it back and making it dead sharp.
As opposed to the combustion chamber.
Yeah. Now, that's not always the case. It really depends on the port angle and the head architecture that you're dealing with. If you have like a coyote head that is a big oval port like that, those two dividers are coming all the way up are actually advantageous because it's separating the two ports. It actually stabilizes it. So if you took those all the way out, that would be bad news. But some ports that have a small opening and really go out for those two valves, you know, those are the ones that'll knock back. Yeah, it really depends on the head. That's something you just got to mess with. The Harley head, the four valve Harley head, knock it back as far as you can get, and it's instant 20 CFM. And it stabilizes the port. It's a lot more stable. All right, guys, we'll call it. Have a good day.